We now consider a modeling application, which is probably more closely related to chemistry, though there are similarities to biomedical applications as well. We're going to consider an aquarium, a big aquarium. It's one that holds 25 cubic meters of water, so quite a sizable one, zoo scale. And what happens with this aquarium is that the water is going to be pumped out, run through a filter, and then pumped back in. What's happening currently is that the water inflow and out is at 10 meters cubed per day. As makes sense, the amount of water that comes in a day equals the amount that leaves in a day, otherwise the tank would either overflow or end up running dry. But what is changing is what's happening inside the water. So what's happening in this scenario is that the inflow is not as clean as it should be. There's actually being ammonia that's in the inflow water because of a breakdown on this end of things. And the concentration coming in is at 150 grams per cubic meter. So you've got a concentration naturally there in the water coming in. At time zero, this water is currently free of ammonia, so it's clean, but we're going to be adding more and more water that's polluted to it, while some of it is going to escape. Some of the water is going to escape and it's going to carry some of the ammonia with it. Let's take a look at how we can break down the mathematical analysis. Find the rate of ammonia entering the aquarium in grams per day. So, key thing for this kind of model again is units. If we have rate of ammonia in grams per day, the two ingredients that go into that, very clearly the concentration matters, because that's grams per meter cubed. How is that moderated though? Well, it depends, or the rate of ammonia in depends as well on how fast is water being poured in. If we had a little trickle of polluted water coming in, well then not much ammonia would make it in. But we have 10 cubic meters coming in per day. And if we check the units out, this works out perfectly. Our meters cubed cancels, and we end up with grams per day. So the rate of ammonia in is going to be 1,500 grams per day. So that's a fairly sizable amount of ammonia going in. What might balance that out is the fact that the volume we're dealing with in the tank is very, very large. Let's see how this all comes together. If the water in the aquarium is well mixed, so the idea is even when we have the contaminants coming in, they mix pretty quickly with the rest of the water. With the water leaving the tank at 10 meters cubed per day, you can imagine sort of a little bubble of water here. When we take it out, it's going to have some ammonia in it. And how can we figure out how much ammonia is leaving the tank? Let's take a look. We're looking for an expression for the rate that the ammonia is leaving the tank. And we're going to need a little feature here. There are S of t grams distributed amongst this whole aquarium. So that's how much in mass of ammonia there is in the tank. So the rate of ammonia out, again, grams per day is what we want. Well, what are the ingredients? Well, we definitely have 10 meters cubed per day. The actual outflow of water is going to have an influence here. So we've got the days. We need to divide by meters cubed. Well, one of the ways we could think about that is to go back to the previous example. What we had here was rate of volume, or rate of water change, times the concentration in grams per meters cubed. If we take that same inspiration and bring it into this model for the rate out, we can do exactly the same thing, except the concentration now comes from two ingredients. Our amount of ammonia in the tank divided by the volume of the tank itself, and that's in grams on top, meters cubed on the bottom, and once again our units work out perfectly, our meters cubed cancels, and we get simply over this whole thing grams per day. Okay, so if we say there's some ammonia in this tank, give it a name S, then we can find the concentration by taking S divided by the volume that's holding all that ammonia, and then we can say, well, how quickly is that going to leave the tank? Well, each cubic meter has this many grams, that's a concentration, and we're losing 10 of those meters cubed every day. Oh, that's a net rate of ammonia leaving. The nice thing about having done all that work is we can now come in to get a net rate. The amount of ammonia in the tank is going to change over time. That's the rate overall. How is it going to be dictated? It's going to be the rate in minus the rate out. That'll be the net rate of change. And we already found that the rate in was 150 grams per day. And we just found out that the rate out was 10 times S over 25. And it's S of t, but once we get into differential equations, we often drop the bracket t because it just gets too long and tedious if we know that S is something that changes with time. Okay, so this is kind of fun, I hope. All right, so the amount of ammonia is going to be going up because ammonia is coming in, and that's also going to be going down or having a negative rate of change because some of it's going to flow out with the outflow water. Sorry, 1500. Now, that's all great, but if you actually look at chemistry, we don't usually talk about the amount of some dissolved quantity. We usually would talk about the concentration. So we do, or it behooves us to look and consider whether we can convert this equation about amounts into an equation about concentrations. Let's see how that plays out. One of the things that we had was the concentration in the tank is the amount over the volume. So grams over meters cubed is grams per meter cubed. So we can easily convert this. That could be replaced by C for concentration. How about the rate? That's the other place where we'd have to change things. Well, the nice thing about what we learned in the fall term is that we can do an implicit derivative here. We can take the time derivative of both sides. And when we do that, well, we get pretty much what we'd expect. The rate of change of concentration is going to be 1/25th the rate of change of the amount of ammonia. The concentration of ammonia is going to be 1/25th of the amount of ammonia. And seeing as we have this in our equation, we can write it out as ds dt equals 25 dc dt. All right. With this ingredient, and with our original differential equation, we can now write it out as 25 rate of change of concentration is going to equal 1500 minus 10 C's, and we can divide through by 25, and we'll get a fairly straightforward analysis there. Let's actually do the calculations though to get some nice numbers. 1500 over 25, better known as 60, and 10 over that, let's keep it simple. We'll just keep it as 2.5 for now in the denominator. And there we go. That is a perfectly good differential equation that tells us how quickly the concentration is going to change in the tank as time goes on. Let's take a look and see where that gets us next. Let's look for the equilibrium and see what happens there. dc dt is 60 minus C over 2.5. Rate of change of concentration is 60 minus the actual concentration currently over 2.5. At the equilibrium, what can we say? Well, that's a concentration that's constant or not changing, so its derivative is 0. And that tells us that 60 minus C over 2.5 equals 0. And if we solve this around, we'll get 60 times 2.5, which is better known as 150 grams per meter cubed. All right. Why does that make any sense whatsoever? We're saying that there's a concentration of ammonia in the tank that would stay constant. Well, it would stay constant if it was 150 grams per meter cubed to start with. Well, that's pretty reasonable because we're adding water, which is contaminated at exactly that level. So if you imagine sort of a dirty pool here with a certain amount of mud or silts in it, and we're pouring in water that's exactly as dirty, well, nothing's going to change. Even though we have water coming out the other side, it's all equally dirty. Nothing changes when it comes to the concentration. So that's a pretty reasonable equilibrium level to find in this scenario. Let's go now and actually find the full solution. We'll take a look at that. Our differential equation was 60 dc dt equals 60 minus c over 2.5. So we separate. And pretty much the whole thing has to come down to the other side. There's not much we can do about that. We'll take the dt up, and we'll end up with 1 over 60 minus c over 2.5 dc's is equal to dt. Then, of course, we integrate. Integrate. All right, right-hand side's easy. T plus a constant. This side, we get, how familiar is this? We get a ln of everything in the denominator in absolute values, but we have this negative 1 over 2.5, negative 1 over 2.5 is what we get next. Okay. Well, what's our next step? We want to solve for c. We're trying to look for a solution, so we're going to solve for c here. When we bring this 1 over 2.5 up, we're going to get ln absolute value of 60 minus c over 2.5. Bring that up, negative t over 2.5, negative c over 2.5. We're going to bring this up as a multiplier, so yeah, I'll leave it that to you. 1 over is going to get brought up as 1 over because it was the denominator on the left. Okay, we're looking for c. We need to get inside that ln, so we're going to exponentiate both sides, treat both sides as the exponent to the base e, and that lets us take care of the ln. The ln and the e are inverses of each other, so they go away, and we're left on the right-hand side with e to the minus t over 2.5 minus, let's be consistent here with what we've done before. If we have a sum or a subtraction difference in the exponent, we can write it as a multiplication down here. And we are in business. Now we're going to do our last little twist and say, let's define a new variable. Oh, this wasn't so good, was it? Let's go back a second here. C was the name of our variable for concentration. I probably shouldn't have reused that. So let's just call that D. Yeah. Okay. So fortunately, it's not going to matter. We're going to get rid of it right now. But we're going to let A equal e to the minus D over 2.5. And again, we're going to have that plus or minus because we have these absolute values on the left-hand side. We don't know when we take them away what's going to happen with the signs. We'll lump that into A. We'll continue this on the next page so it isn't too cramped. We make that conversion, we'll have 60 minus c over 2.5 is e to the minus t over 2.5 times A. Okay, still honing in on c, so we'll bring this to the other side, bring that over here. We'll have 60 minus A e to the minus t over 2.5 is c over 2.5, positive because we moved it over. And finally, our solution, concentration, that's what C is here, is going to equal 2.5 times 60 minus A e to the minus t over 2.5, better known as 150 minus 2.5A e to the minus t over 2.5. Okay, that is a wonderful solution. We can add one more ingredient. We're also told that C of 0 equals 0. In other words, the concentration in the tank was 0 when we began, and we just started pouring in polluted water. So if that's the case, then we would have 0 on the left equals 150 minus 2.5A e to the time here is 0. And we can bring all this is 1 then. Moving the 2.5A to the other side, we get that equal to 150. Now, if you look at actually what we want to evaluate, we actually want 2.5A in our equation, so let's actually leave it as is. C of t is 150 minus 2.5a. 2.5a is another 150 minus t over 2.5. And that is a perfectly wonderful solution to this differential equation up here. We can predict what the concentration in the tank is over time and use that to answer some questions about the potential future health of the fish. In particular, if a concentration of 0.1 milligrams per liter, or converting the units here to 1,000 grams per meter cubed, if that's a danger level, we might want to know how long will it take before this 150 milligram or gram per meter cube water coming in will burst through this barrier and cause some sickness amongst the fish. Well, with our solution, this is straightforward to find. We have 150 minus 150 e to the minus t over 2.5. We're interested in the t when c is equal to 100. So this just becomes a standard equation setup. Let's set c equal to 100 and solve for t. And working through the calculations now, there's no calculus anymore. This is straight manipulation of equations. We can bring the t stuff over to that side, the 150 on that side. And 150 minus 100 is just 50. So e to the minus t over 2.5 is 50 over 150, or just 1/3. 50 over 150 gives us a third left. Now let's actually move that over a hair, because our next step is going to be to try to get rid of this exponential. We want t, we've got an exponential of that. We're going to take the ln of both sides. And as we've seen in other examples, the ln and the exponential are inverses, so doing them both to the same input cancels them out, and we're left with the ln of 1/3 on the right. And last but not least, t is going to be 9 minus 2.5 ln of 1/3. And if we type that into our calculator, we get approximately 2.75, and the units of time we've been using throughout is days. So what we've just found is concentration that starts at 0 of ammonia. Over time it's going to grow towards 150, the equilibrium. But that was all stuff we could determine from the differential equation. But what we couldn't do without the solution is find out how long it'll take to reach some intermediate value, 100 grams per meter cubed. So we've got 2.75 days before the toxic level is reached. And just in terms of a graphical sense of that, what we have is our equilibrium level at 150. We're starting at 0, but the toxic level is down here at 100. It'll take us, let's have it happen here, it'll take us 2.75 days to reach that level there. It'll exponentially decay towards 150, but the crossing point of the toxic level will be a hair under 3 days later after the filter breaks down originally.